Every day, 178 million trips cross bridges the federal government classifies as structurally deficient, not sound enough to pass, yet still open to full traffic. The American Society of Civil Engineers scored the nation's bridges a D+, a grade that has barely moved in years. Behind it, 617,000 aging structures, a repair backlog exceeding $100 billion, and a crisis hiding behind every American commute. The distance between what engineers know about these bridges and what you've ever been told is where this story begins. Every 4 years, the American Society of Civil Engineers releases a National Infrastructure Report Card. This system translates thousands of pages of highly technical data into a single, understandable grade for taxpayers and policymakers. Since 2017, America's bridges have held a D+ grade. A D+ grade indicates that a significant portion of these structures are in poor condition, showing advanced deterioration and operating with a heightened risk of failure. When the Society issued its report card, other public systems showed progress. Public transit, drinking water, and energy systems clawed their way upward, lifting the nation's overall infrastructure grade to a C- in 2021. Yet, the grade for bridges remained completely stagnant. They did not budge from the D range. This stubborn score shows that while other public assets slowly recover, the concrete and steel carrying millions of vehicles daily are left behind. Spread across the United States is a massive network of roughly 617,000 bridges. As of 2022, federal records classified about 42,000 of these structures as structurally deficient. This designation means that at least one key load-bearing component, such as the deck or the concrete support piers underneath, has degraded to a poor state. Rather than being isolated to a few remote areas, this structural wear is distributed throughout the entire national transit system. Statistically, 1 in 3 American bridges now requires significant repair or complete replacement. Many of these spans are aging simultaneously. The average bridge in the national inventory is 44 years old, meaning a large portion of the network was built decades ago to handle much lighter traffic than it carries today. This deterioration directly affects daily life. For a parent driving children to school or a commuter heading to work, these statistics materialize as the concrete overpasses and river crossings they cross twice a day. The wear is silent, ongoing, and embedded in the daily routines of millions of people who assume the pavement beneath them is sound. To evaluate bridge safety, the Federal Highway Administration relies on a strict 0 to 9 condition scale. National standards require inspectors to assess 4 primary areas: the deck, which supports the actual roadway; the superstructure, which bears the immediate weight of the traffic; the substructure, consisting of the piers and abutments that anchor the bridge; and any culverts running underneath. If an inspector rates any single one of these major components as a 4 or lower, the entire bridge receives the federal classification of structurally deficient. A rating of 4 indicates that the component is in poor condition, showing advanced decay, cracking, or material loss. This classification does not mean a bridge is in danger of immediate collapse. Instead, it serves as an early warning, indicating that an essential load-bearing element needs rehabilitation or replacement. While waiting for these repairs, federal rules allow these deficient bridges to remain legally open to full traffic. This operational status keeps the aging network integrated into daily routines. Every day in America, commuters, school buses, and commercial trucks make roughly 178 million trips across these structurally deficient bridges. These drivers move at highway speeds, completely unaware of the degraded support systems resting just feet below the pavement. On August 1st, 2007, during the evening rush hour, the 8-lane steel truss I-35W bridge in Minneapolis suddenly fractured and plunged into the Mississippi River. The disaster killed 13 people and injured 145 others. At the moment of the failure, the span was carrying part of its daily load of 140,000 vehicles, alongside heavy construction equipment parked on the deck for resurfacing work. For 17 years leading up to the disaster, the National Bridge Inventory had classified the I-35W bridge as structurally deficient. Its superstructure score fell to a 4 in 1990, yet the physical failure originated from an error made 40 years earlier during construction. Investigators from the National Transportation Safety Board discovered that the bridge's steel gusset plates, which joined the massive truss members together, were designed too thin. At just half the required thickness, these undersized plates from 1967 held the structure together until the cumulative weight of traffic, concrete modifications, and construction materials ultimately caused them to buckle. The Minneapolis disaster proved that structural deficiency classifications warned of real, physical dangers. It forced the first serious nationwide bridge safety conversation in decades, forcing state and federal agencies to reevaluate how they assessed the load capacity of non-redundant steel bridges across the country. Before dawn on March 26, 2024, a container ship lost power and struck a primary support pier of the Francis Scott Key Bridge in Baltimore. The collision triggered a catastrophic chain reaction, causing the entire continuous steel truss span to collapse into the Patapsco River within seconds. 6 construction workers who were repairing the roadway at the time were killed. The disaster instantly severed an essential freight artery in the Northeast. Prior to the collapse, the bridge carried 30,000 vehicles every day. With the crossing destroyed and the port of Baltimore blocked, regional shipping networks were thrown into chaos. Rerouting freight and commercial trucks around the harbor cost the economy an estimated $15 million per day. While the destruction resulted from an external collision rather than structural decay, the immediate fallout demonstrated the extreme fragility of the nation's supply chains. The event temporarily reignited congressional debates on infrastructure protection, but the political momentum quickly stalled, producing no new federal legislation. The federal government estimates that clearing the backlog of structurally deficient bridges requires $125 billion. Yet normal federal funding across all programs averages only $16 billion per year. At this pace, clearing the existing backlog would take decades, even if no other bridges deteriorated in the meantime. To address this mismatch, the 2021 Infrastructure Investment and Jobs Act allocated $40 billion specifically for bridges over 5 years. While this represents a significant cash injection, engineers estimate it covers only 30% of the actual national need. This leaves 70% of the repair bill completely unfunded. For everyday drivers, this mathematical gap means that local authorities cannot fix every decaying bridge. Instead, they must prioritize high-traffic highways, leaving thousands of rural and neighborhood crossings to decay further. The funding simply does not match the physical reality of the concrete and steel. When money is scarce, states are forced to defer routine maintenance, turning minor concrete cracks into major structural failures down the road. Every deferred repair increases the ultimate cost of keeping these crossings open. The physical decay of America's bridge network is highly concentrated in specific regions. Iowa has the highest percentage of structurally deficient bridges at nearly 20%, representing over 4,400 poor crossings. By total count, Pennsylvania leads with over 3,400 deficient spans, while Rhode Island, West Virginia, and South Dakota round out the worst 5 states. While urban highway projects dominate the national news, the true weight of this funding neglect falls on rural communities. Local agricultural bridges receive far less funding and attention, yet they carry the food supply of the entire nation. For a family farmer in rural Iowa, hauling thousands of bushels of grain, a deteriorating bridge is a daily financial threat. When inspectors post strict weight limits on these aging crossings, heavy trucks are forced to detour miles out of their way, wasting diesel, delaying time-sensitive harvests, and driving up food transportation costs. In Pennsylvania, a regional trucking company saw its annual operating costs spike by $1.2 million after the Route 322 bridge received a 10-ton load limit, forcing a 12% drop in cargo volume. Across the country, these weight-restricted crossings add $28 billion annually in freight transport expenses. For everyday motorists, the damage translates to roughly $1,000 each year in extra fuel and accelerated vehicle wear from avoiding deteriorated spans. When a bridge degrades to the point of emergency closure, the immediate financial burden shifts to county and municipal taxpayers. Local governments spend an average of $100,000 per day solely to manage these sudden detours, pay for traffic control, and reroute emergency vehicles. This constant wear on local budgets and household expenses means the national bridge deficit is not a distant problem. It is a daily invoice already being paid by businesses, family farms, and commuters. While economic losses pile up on the surface, a silent physical decay unfolds beneath the asphalt. Most bridge failures develop slowly over years, rather than occurring in a single, sudden instant. They are the result of quiet, cumulative degradation that often remains completely hidden until a critical limit is reached. Inside concrete structures, steel reinforcing bars face a destructive enemy. In northern states, winter road salt seeps through the porous concrete, accelerating the chemical corrosion of the steel underneath. As the internal rebar rusts, it expands, fracturing the surrounding concrete from the inside out until the outer layers begin to flake and fall away in a process called spalling. But the most severe threat is completely submerged. Turbulent water flowing past a bridge pier gradually sweeps away the supporting soil and sand around the foundation. This underwater erosion, known as scour, slowly hollows out the riverbed. Scour is the leading cause of bridge collapses in the United States, triggering approximately 60% of all failures. Detecting these invisible threats falls to the bridge inspector, who must examine what the public cannot see. Inspectors begin with basic visual assessments, walking the deck and scanning concrete columns for cracks, rust stains, or peeling paint. While effective for surface decay, this method misses everything beneath the exterior. To check foundations submerged in fast-moving rivers, specialized diving teams must descend into the water, feeling for structural damage in near-zero visibility. When the interior of steel or concrete must be checked without causing damage, technicians use non-destructive testing. Ultrasonic instruments send high-frequency sound waves through steel beams to detect hidden internal cracks before they reach the surface. Similarly, ground-penetrating radar scans the roadway, locating voids and moisture trapped deep within the concrete deck. Each tool reveals a different layer of a bridge's condition, but every method has blind spots that can leave structural decay undetected. Federal law mandates that public bridges undergo safety inspections at least once every 24 months. Yet this regulatory safety net contains deep operational gaps. While surface-level decks are checked on schedule, complex underwater inspections of riverbed foundations are frequently deferred, sometimes for up to 6 years. This backlog is worsened by a severe, nationwide shortage of certified bridge inspectors. With limited public personnel, state agencies increasingly rely on private contractors, leading to significant variations in inspection quality from state to state. But the greatest breakdown occurs between detection and action. The 2007 Minneapolis disaster exposed this vulnerability. For 17 years prior to the collapse, inspectors documented the structural decay of the I-35W bridge in the National Bridge Inventory. Those written warnings sat in databases, but the institutional process failed to translate paper reports into physical repairs. This gap reveals a sobering truth. Identifying a failing component does not guarantee a crew will show up to fix it. For the millions of Americans driving to work or sending their children off on school buses, these engineering concerns exist entirely in the background. Most drivers have no idea what their daily overpasses are named, let alone how they are rated. While the federal government publishes detailed safety data, this information remains buried in complex databases that require specialized knowledge to decode. There is no simple, searchable national database where a commuter can type in an address to verify if a local river crossing is sound. Instead, the national D+ grade is experienced in complete anonymity. It is the familiar overpass overhead and the neighborhood bridge crossed twice a day, trusted implicitly, even as the steel beneath the asphalt quietly degrades out of sight. Much of this vulnerability is the predictable result of a timed clock. Between the 1950s and the 1970s, America built the majority of its modern bridge network in a massive burst of post-war construction. Engineers designed these structures with an expected 50-year lifespan. Today, that generation of infrastructure has quietly expired. The average bridge now operates decades past its intended engineering limit, while the oldest structures exceed their design lives by nearly 40 years. While federal programs and state matching funds exist in principle, the capital required to systematically rebuild this network has never been fully committed in practice. The physical reality of concrete and steel remains unchanged. It leaves the country with a fundamental, unresolved choice: whether to invest and rebuild before the next collapse, or continue to pay the price only after a disaster forces our hand. To follow this ongoing investigation, subscribe now. Every journey across an aging span is a silent negotiation with time. A structurally deficient label isn't an immediate threat, but a severe warning. We can invest to secure these crossings today, or wait for the next disaster to force our hand. The cost of neglect always exceeds the price of repair. Subscribe for more in-depth investigative documentaries.